Today, we're going to talk about capnography. Capnography is the monitoring of carbon dioxide coming out of your patient. So we can use this for diagnostic purposes. When you're using this for CPR performance, so knowing how well you are doing compression. So if we're doing compressions very well, carbon dioxide readings in capnography will increase. We can use it for endotracheal intubation confirmation. So not only do we have lung sounds bilaterally and no epigastric sounds, but my capnography waveform is normal and I'm getting a good capnography reading. And then when we have a patient on mechanical ventilation on our ventilator, we're definitely going to be monitoring our carbon dioxide and our capnography waveforms. Our monitoring of carbon dioxide can be both qualitative and quantitative. So quantitative gives us a number, gives us a waveform. Qualitative isn't quite so specific, but can give us a color, let's say. So on the left here we have a qualitative device, and when we breathe, let's say we hook this up to an ET tube, we've just intubated our patient, we breathe through our BVM, we're seeing, are we getting any carbon dioxide back? And with this device here, we want a yellow color. So yay for yellow is what we're looking for. If it stays purple, we aren't really getting any carbon dioxide back. What we have really nowadays and more easily accessible for most EMS systems is this quantitative capnography system, where we get a waveform right here. See down below, we get a waveform, and we get a number right here. We see 37. So remember that our normal CO2 readings are 35 to 45, and that's from an ABG, an arterial blood gas. But our capnography readings, our end tidal CO2 readings, correlate very closely to our arterial CO2 reading. So the reading you get off of this monitor here, this 37, will be very, 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 very close to the ABG that you pull and read a carbon dioxide reading off of that lab value. So because of that, because this waveform and this number correlates very closely to our ABG, even though we're not pulling an ABG, it's just this end tidal CO2 value. We're going to focus on this a little bit more, and that CO2 waveform, or what I call our capnogram. What we're looking for the height of it, we're looking for the frequency, the rhythm of it, where our baseline is, right? So where is our baseline? Does it come back to baseline? Does it not? And then the shape of it. So we're looking for the height right there. We're looking for the frequency, looking for the baseline, looking for the shape. Now let's talk phases of that capnogram. So we had this shape of this wave that we saw right here, right? We've got this like little box shape, and what does this box shape mean? Well, we've got phase 1, phase 2, phase 3, phase 0, and it's kind of weird, right? So just like our action potential, we've got phase 0 and phase 1s and phase 4s, and it's just kind of weird. So we need to think about, when are we exhaling CO2, because that's what this wave is doing. That's what this machine is doing, is measuring carbon dioxide. So when it goes up, we've got some carbon dioxide measurement, right? So let's start with with phase 0, because I think that intuitively that's kind of the easiest way to start, is we inhale. And as we inhale, we're obviously not exhaling any CO2. So we've got this inspiratory downstroke. So we're inspiring, and in phase 1, we're this inspiration, I've just taken a breath in. So if I'm taking a breath in, I'm obviously not breathing out any carbon dioxide. And then we get to phase 2, right? Our expiratory upstroke. I start to breathe out CO2. I get to phase 3, I get this plateau. Just like in your action potential, we've got this plateau. Well, with phase 3, I've got this, I'm breathing out, right? I'm breathing out, I start to breathe out, then I plateau. And phase 3 is my plateau. But that plateau is kind of upswinging, and I get to a point, and that's where we measure our end tidal CO2. And that becomes really important because this point right here is my end tidal CO2. So think about that, my end tidal. So my tidal volume is just my in and out. So at the end of my out, at the very end of my out, is where we are measuring that carbon dioxide level. Now you might be wondering, yeah, fine, that's the end tidal CO2, that's the end of my tidal cycle, right? But there are these like weird little, I don't know, swooshes right here on this wave. And it's alpha and beta. Well, we've got an alpha angle and a beta angle. Well, these angles, so we still have an end tidal CO2. Depending on, no matter what condition you're in, you have an end tidal CO2. But depending on what condition you're in, your alpha angle and your beta angles will change. So as we move through different kind of diagnostic categories, as we move through different conditions, we might see that alpha angle and that beta angle. So that beginning tidal wave, or excuse me, that beginning tidal angle and that end tidal angle are going to change. So not only do we have to, are we measuring what this end tidal carbon dioxide level is, we're measuring the angles, and we're paying attention to the angles, that both that alpha angle and that beta angle, depending on your medical condition. So let's talk patterns. I'm looking at our capnograph patterns, our capnography patterns. This is normal. This is a normal pattern that you want to see. So I am inspiring down to baseline. I'm starting to expire. I reach end tidal right there. This is where my my reading comes out on my monitor. I inspire again, come down, expire, kind of comes up a little bit, right? This is normal. This is what you want to see. You want to see a little bit, so your alpha angle, your beta angles, a little bit different. You want to see a little bit of a slope right there, comes back down to baseline, and then comes back up. This dotted line right here, we'll say this is 40. We'll say this is 40 millimeters of mercury. So this is a normal capnograph. Ooh, let's go away from normal. So let's talk about hyperventilation. We're going to go like one hyperventilation at a time. So normal breath right here, start at baseline. Yay! Kind of breathe out, come up to 40. We're good. Inspire, back down to baseline, and then we start going quicker and quicker and quicker and quicker. You see these capnographs, these waves, are getting a little bit closer, a little bit closer, a little bit closer, a little bit closer, and the height of them is going down because as we breathe faster and faster and faster, we're no longer at 40 millimeters of mercury, right? Our CO2 is no longer 40, which is our dotted line. We're going lower and lower and lower. We're breathing off more and more CO2. So with each breath, I go, not only are my waveforms closer and closer together, but they're getting shorter and shorter and shorter and shorter because my end tidal is going down. Remember, my end tidal is here, this beta angle. End tidal is going down and down and down, and now instead of 40, now I'm at, I don't know, 26, let's say, right here. But we're still worried about our alpha and beta angles, and our alpha and beta angles are remaining consistent. They're remaining constant. So the wave looks the same. It's just shorter, right? Shorter in a temporal sense. They're closer together, and they're getting shorter and shorter and shorter in a height sense. So they're closer together, meaning I'm breathing faster. They're getting shorter in height sense, meaning my end tidal CO2 is going down. So this is a typical simple hyperventilation capnography waveform. On the other side of hyperventilation with the hypoventilation, again, the waveform looks the same, right? Our alpha angle or beta angle is the same. We're good there. They're just spaced out. A lot more spaced out. And my end tidal CO2, which is measured here, 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 and well, would be here, is going up and up and up and up. Not because the waveform is changing, but because the frequency is changing. So I've got hypoventilation. So this is a telltale sign of hyperventilation, going down, but the wave looks the same. Hypoventilation, it's going up, but the wave looks the same. Now some fun ones. So we went through hyperventilation, hypoventilation. They look normal, right? Whoop. They look normal. That's our normal. Well, let's go into some fun like asthma COPD. And all of a sudden we don't have like a nice square. Or even like a little upslope square like we should. We've got this, what we're going to call a shark fin. Womp, womp, womp. Right? We've got this shark fin. So it's Shark Week here, here at EMC. And why is this? So our downslope is our inspiration. Right? So I can breathe in just fine. I have an asthma attack. I can breathe in just fine. I have an issue with my bronchodilation, and I have an issue exhaling. So think about your asthma patient. Think about your COPD patient, and their pursed lips, right? They're trying to force out. They're trying to get out this air. That's their issue. They can breathe in just fine. So this inspiratory wave, this inspiratory angle, this beta angle, is just fine. But then they've got like 0 alpha angle. And they're trying to push this out. And because of that, they are trapping CO2. So their end tidal CO2 is up here. It's above this 40 line, right? So CO2 should be 40. Let's say that's our happy number. CO2 is 40. We're up here, right? So as I inspire, I'm fine. Go back to baseline. And then I force air out. And it takes a while to force that air out. And now I'm up here. So this is your quintessential, this is your standard asthma, acute asthma, and COPD exacerbation capnography waveform. If you ever see this waveform on your capnography, it means you're breath stacking. It means you're breathing too quickly for your patient. It's most typically. Normally, patients don't do this on their own. Just normally. This is us via BVM. This is us via ventilator. We're just breathing too quickly for them. So we've got a normal looking wave, right? So kind of squarish looking, kind of squarish looking, kind of squarish looking. But every CO2 level, right, end tidal, right here, this beta wave, right there, is going a little higher, a little higher, a little higher, and our baseline keeps going up and up and up. And what we're doing, or what we're not doing, is we're not allowing for full expiration. So we're in essence, we are trapping air in our patient's lungs for them. So our baseline goes up, goes up, goes up, goes up, even though we're providing a normal breath, even though they're handling this normal breath, our baseline is going up and up and up, and we just need to reevaluate our ventilatory rate, maybe our ventilatory volume, and readjust so we can bring our baseline down, back down, so we can get our end tidal back to that dotted line, that 40. This is always an issue of our ventilated patients, or intubated patients, whether they're BVM or ventilated. So how to quickly fix this? You know what? Disconnect the ventilator. Pull off your BVM. Exhalation is a passive process. Pull it off for a few seconds. Let that passive exhalation occur, and then start your ventilations again. The worst nightmares of our worst nightmares is an esophageal intubation. So we think we've intubated the trachea, and maybe we haven't, right? So did I hear lung sounds? Did I not? I don't know. Did I hear epigastric sounds? Did I not? I don't know. Let's hook them up to capnography. And what do we see? Well, we don't see a nice wave, right? We don't see this nice normal wave. We don't see this nice little box-shaped wave. Instead, we see this. So we've got no CO2 coming. We might have some in the beginning, and then it just kind of fades away into nothing. That is an esophageal intubation. Pull that tube right away, re-intubate, and try again. One last waveform for you is a Curare clef, and Curare speaks to our paralytics, so derived from Curare. So our paralytics, we think sucks, we think vecuronium, recuronium. So we've got this waveform. It kind of comes up, right? So we're expiring, starting to come up. It should be going, up to about 40 right here. This dotted line should be going on to about 40, and we got this ka-junk, right? This little cleft. And it takes another breath. It goes right. What this tells us is we've got expiration, right? We're expiring, and then what this tells us is this negative deflected line is a little bit of an inspiration. So our patient just inspired a little bit, and then didn't. And then they expire, right? And then inspire a little bit, and then didn't. We've got them on a ventilator, but they're doing this, right? If they're on a ventilator, why should they be inspiring in the middle of an expiration? So our ventilator is in complete control. Why should they be taking a breath in the middle of an expiration? Well, that's because their paralytic is wearing off. Their sedation is wearing off. If you ever see this, immediately sedate, immediately paralyze. If your patient is on a paralytic, immediately paralyze. If they're on propofol or etomidate ketamine, some heavy kind of sedative drip, up that sedative drip. So we want to sedate, we want to paralyze. So this Curare cleft is a sign that your patient is starting to buck the tube before physically bucking the tube. So we're going to see this before they start any physical signs of fighting the tube. We're going to see this. So if you see this little cleft, as an immediate response that we should be giving an additional dose of paralytic, we should be getting an additional dose of any sedative. Whatever is keeping your patient down for that transport, we should be upping the dose. If you have any questions, comments, concerns, or cuss words, please let me know.